Hello everyone, my name is Artemy Malkov. I am the founder and CEO of Data Monsters, an AI research lab and consulting company. We are NVIDIA's preferred professional services partner, and for more than 10 years we've been working with large companies and help their innovation divisions and internal product teams to start their AI journey, pick the right set of technologies and hardware, and complete their pilot projects successfully. Today, we will be speaking about Edge AI in manufacturing. Manufacturing deals with machines. Manufacturers already use robots to reduce manual operations. Not necessarily steel robotic arms, but any types of smart devices and algorithms. Examples are smart scheduling, predictive maintenance, computer vision, and so on. One of the great uses of computer vision in a factory is the problem of visual inspections and defect detection. Production lines are often high speed, and human workers simply cannot manually check every produced item, especially for low cost products. Therefore, sampling manual checks do not cover all produced items, and defects are detected down the chain during packaging, distribution, or even worse, already in the hands of the client. The food industry is just an example of mass production with low-cost items, but very large volumes. Manual checks here are very tedious, but consumers are really sensitive to the quality of what they eat and drink. So even a small fraction of defects in the food production process can have a very negative impact on the brand and on relationships with the retailers. At the same time, the scale of the food industry is simply enormous. For example, according to various estimates, more than 50 billion aluminum cans of food and drinks are consumed annually in the United States. So let's look closer and understand how defects occur. The packaging line runs at a very high speed. The slightest hindrance or desynchronization of the mechanisms can cause physical disruption, and machines start damaging aluminum cans. The whole batch of thousands of cans may be wrinkled if the disturbance wasn't timely identified and the line wasn't stopped. Here you can see the main machines of the beverage packaging line. The conveyor brings empty cans to a machine called the filler, and the beverage also gets there through pipes. It takes one spin of a large filler wheel to pour the beverage into an empty can. Then the simmer machine seals the can with the lid at a speed of over 100 revolutions per second. Next, the sealed cans go along the conveyor to the pasteurizer for heat treatment. After that, they are labeled and packed in boxes. And finally, the boxes are put together on pallets for further delivery to the warehouse. Most physical defects occur in areas of the highest speed, specifically the filler and the simmer. That's why manual and automatic inspections are usually placed right after the simmer machine. This is the right place for the computer vision solutions as well. In my entire data science career, which has lasted for over 15 years, I have found this problem, real-time defect detection, really challenging and exciting. Just think of it. The cans are moving 30 cans per second. Four industrial cameras are capturing 150 images every second. It's more than a gigabyte of data per second. So the deep learning model has to detect a defect in less than 5 milliseconds. Do your AI models run that fast? And simple computer vision models don't work, by the way. The package design may vary from batch to batch. The cans are covered with moisture, they are basically wet. They may even explode. To collect the dataset, you need to collect samples of defects of different types, but some defects are really infrequent. So you need to sit and wait at the factory in a distant small town for many weeks until you collect samples enough to assure the predictive quality of the algorithm. This is great, guys. I really like it. Yeah. And we should also bear in mind that ideally the computer vision solution would not require any changes in the existing conveyor setup. There are a lot of constraints. For example, it must be waterproof, it requires some physical space, which is not always easy to find on the real conveyor. There must be cables, connectors, lighting, and so on. By the way, the photos of the cans are really dark. That is because the exposure time of the camera is only 50 microseconds, not milliseconds, it's microseconds. So imagine you get terabytes of almost black photos of hundreds of thousands of wet and blurry cans every day, and you cannot transfer these terabytes of data to a central cloud or a data center because the factory is placed in a small town and the internet bandwidth is 1 megabit per second or even less. It's just 1,000 times slower than you need for your project. However, there is a solution, and that solution is called Edge AI. That means you literally need a supercomputer in that small town at a factory 20 feet away from the simmer machine. And the supercomputer should be equipped with GPUs, of course, to deal with the data throughput with these terabytes of image data. Importantly, it's not just one supercomputer, it is the whole fleet of supercomputer devices solving high-performance tasks on each production or packaging line or in the field. These devices are going to be managed by NVIDIA Fleet Command, a new tool in the NVIDIA ecosystem, which works fine even in a low bandwidth environment. To build a solution, we use an NGC-ready server. You can find the list of these servers on the NVIDIA website if you need. We have 4 industrial cameras connected to the server, and it runs containerized image pre-processing, high-performance inference, anomaly detection models, and stores data for local training. The EGX Manager allows centralized device management, health monitoring, and updates. In our case, we have an ensemble of computer vision models, and they are deployed to the edge servers by EGX Manager. They both improve themselves at the edge and send back newly discovered defects and anomalies for manual analysis and model improvements. As a platform, we have NVIDIA Metropolis under the hood. This is a quite new part of the NVIDIA ecosystem, but it already has a lot of applications. Smart cities and retail are the most common use cases. Here we use Metropolis platform for defect detection at the factory. Metropolis is a combination of tools for secure edge computer vision applications. In our case, we use DeepStream SDK responsible for the image processing pipelines and messaging, and TensorRT, which makes deep learning model well optimized for the edge devices. Okay, let's dig deeper and understand how the solution works in more detail. I would like to mention one of our clients with whom we've been working for several years so far. We have happily implemented about 10 projects together, and it is one of the largest food companies in the world, ABI Inbev. We're glad to work with a company like this. Yeah, it's not a Silicon Valley company, not Google nor Amazon, but they are open to innovations, energetic, and ready for discoveries. So let's take a closer look and get some practical insights about real-time defect detection. The architecture has 3 main pipelines. The first part is image capturing. The data comes from high-speed cameras at about 100 frames per second. Cameras require special conditions and lighting. Then the images go through the DeepStream pipeline. It runs pre-processing and computer vision models and then sends alerts to the dashboard. And finally, there is a model update cycle. As I said, the internet connection to the factory is really slow, so we cannot transfer all the images to our data science team. So we upload only discovered anomalies to analyze and update the models. We optimize the model with TensorRT and add them to the NGC registry. So the EGX manager can deploy the models back to the edge server. Here are the image capturing conditions. Given the conveyor speed of about 8 feet per second, we have to detect dents and wrinkles on aluminum cans that are smaller than 1/10 of an inch. We have to limit the motion blur to that size. Simple calculation gives us estimated exposure time limit of about 40 microseconds, which corresponds to huge shutter speed of 1/25,000. With this shutter speed, we still need to control as much of the can surface as possible, which means that we must capture 30 frames per second from 4 angles. That produces more than 100 frames per second in total. Environment conditions at the factory do not allow installing edge compute devices in proximity to the cameras, so the minimal distance to install the compute server is over 80 feet away. With these requirements in mind, it was clear that standard video surveillance cameras won't work. Video cameras produce highly compressed video streams using H.264 codec. NVIDIA DeepStream technology decodes these video streams and feeds the decoded bitmap frames to the deep neural network without the need to pass them around between the host RAM and the GPU RAM. However, standard video cameras cannot meet our requirements. For example, they feature a rolling shutter which scans an image from the CMOS sensor line by line. During this scanning process, there is a high-speed motion distortion. Shutter speed of 1/25,000 is typically unavailable for video cameras. That's why we had to choose industrial computer vision cameras that operate just like photo cameras, shooting frame by frame. These cameras feature global shutter as opposed to the rolling shutter. That eliminates high-speed motion distortion. Between many industrial cameras, we choose one that uses GigaVision protocol based on industry standard Ethernet cabling infrastructure. So there is no need for hardware image grabbers. Here is the image processing pipeline. We get data through Gigi protocol from the cameras and use separate containerized image grabber applications for each camera. Image grabbers operate at the edge computing nodes. They capture frames from the cameras, encode the frames into JPEG bitstream, and transfer it to the DeepStream application using 0MQ, a high-speed, low-profile message queue. DeepStream pipeline is built up with a set of standard DeepStream plugins. The first one, NVJPEG Deck, decodes JPEG bitstream into RGBA bitmaps using CUDA Toolkit with hardware acceleration. The second plugin packs incoming bitmaps from multiple sources into a batch. It waits for a given timeout before forming the batch. If the complete batch is formed before the timeout is reached, the batch is pushed down the stream. If the timeout is reached before the complete batch can be formed, it just packs the available input buffers and pushes them forward. The third one, NVInfer, performs batched inferencing using the segmentation model. This is where our defect detection magic happens. NVInfer uses TensorRT inference to run optimized deep learning models. The fourth, NVMessageConv, generates the payload metadata based on the inference results. Finally, the fifth plugin, NVMessageBroker, sends payload messages to the server for further integration into BI applications and factory dashboards. Traditionally, most of the deep learning models are supervised. This approach is currently widely adopted in the industry. If you Google defects detection, you're likely to get thousands of examples of segmentation models predicting dense regions of defects in the photos, videos, and X-ray scans. There is one problem with supervised deep learning. The dataset should be well balanced and large. I mean, we need at least a few hundred examples of each kind of defects, and the number of these training images with defects should be equal to number of images of good products having no defects. This is hard to obtain, especially for the diverse variety of defects and multiple package designs. Jan LeCun, one of the inventors of convolutional neural architectures,
suggests that the self-supervised learning is the next big thing to solve computer vision problems. One of the problems we've been working on for the last several years is how to apply self-supervised learning to anomaly detection. We get a lot of data, terabytes of images that we cannot even transfer back to the research lab. Yeah, that's because we are limited by the internet bandwidth. So, unsupervised learning allows us to train on site and to predict the noise can images from the real life images where the cans can be randomly rotated, covered with water drops, and so on. We utilize the fact that 99% of the time the production line works fine and we get defect-free samples to train the network. As soon as we see that the reconstruction error of a newly captured image drops below the threshold, we switch the model to inference, anomaly detection mode. In our experience, when using NVIDIA GPUs, a few hours of footage captured on the production line is enough to train the anomaly detection model. In the inference mode, the model reconstructs the appearance of the cans and compares them with the actually captured images. When there is a defect, the reconstruction error increases, so we can detect it and fire an alert. There are many advantages of this approach. To name my favorite, there is almost no need for data labeling. The whole deep learning system turns into a magical device. Turn it on, let it self-train, and expect the anomaly detection alerts. That sounds easy, but it's not easy to build at all. It took us several years and a little bit of black magic to solidify the solution. And of course, this approach requires powerful hardware for federated training on premises. Yeah, you know what I mean. The more you buy, the more you save. Anyways, even with the self-supervised approach, we need a feedback loop with the central research lab. So we have to send a small fraction of captured and processed images to the central online storage, where the scientists can monitor the performance of the models and improve self-learning algorithms. After the scientists have finished their magic, it's time to prepare the models for the edge inference. And here comes the TensorRT optimization. This is an important part of the process, especially if we decide to use lightweight edge devices like NVIDIA Jetson. Even in our case, and here we use NVIDIA T4 GPUs, we really need that optimization. As you might remember, we are working on a high-speed conveyor with 100 high-resolution images per second. That feels like a lot of data, right? And ideally, we need to detect the defect in real time and push the damaged can into the trash container. So everything should be done in milliseconds. TensorRT basically does several things. Let's say we use TensorFlow framework for deep learning models. TensorFlow creates a computational graph, the sequence of neural network layers. While training, the graph is used to update neurons via forward and backward propagation. After you finish training, the neurons won't change anymore, and the model is what's called frozen. So instead of computing a sequence of operations for each layer every time, it's possible to pre-compute it once and have just one tensor, a combined layer, in the computational graph. This is exactly what's called layer fusion in TensorRT. It finds the nodes of the graph that only one operation is enough and fuse them together. That made no sense while training because you want individual neurons to be changed on backpropagation. But after the model is frozen, it is perfectly fine to fuse the layers and forget about the individual neurons for the sake of performance. TensorRT also reduces the floating point precision. Scientists like high precision, like a FP32 while training, but after the model is trained and frozen, FP16 is okay. It requires less memory, it runs faster, and takes advantage of FP16 tensor cores on GPUs. Finally, TensorRT does kernel auto-tuning, adapting the computational kernels to the target GPU platform. In our case, it's adapting the convolutional kernels to the T4 card.
The final step of the pipeline is to update the models on the edge devices. This is where NVIDIA Fleet Command comes into play. Suppose we have 7 factories and each has 5 production and packaging lines. We have the whole fleet of the edge computers equipped with T4 or Jetson GPUs. So, how do you deploy and manage the models and apps on those devices? NVIDIA Fleet Command does that for you. It uses NGC registry for the models and apps. You basically create a Helm chart that describes the set of Kubernetes resources you want to have on the target edge devices. Equipped with this information, NVIDIA Fleet Command now can deploy the models and plugins to the edge devices. Like in our case, we have an NGC ready for Edge Dell server with 2 T4 GPUs. The platform provides us with an edge-friendly, secure version of Kubernetes for every device and makes it simple to deploy and monitor the whole fleet of devices from one single cloud-based user interface.
At Data Monsters, we've been designing and developing AI solutions for more than a decade. Having all my experience, I can tell that with Edge AI, literally, we stand today on the edge of a new frontier. In the next few years, we'll see a lot more intelligent devices at home, in the factories, and smart cities. It's a lot more challenging for designers, researchers, product managers to organize the intelligent interaction of those devices, keep them up to date, make them share their locally acquired knowledge among the rest of the network, especially under severe physical constraints. It's hard, however, there is no other way. And those businesses who are open to experiments, to discoveries, to gains and failures, they will transform the way they make money, run their processes, and make their clients happy. Those companies will survive the AI revolution and will prosper. Thank you for your attention. That was Artemy Malkov, the CEO and founder of Data Monsters. If you need any help or advice if you're building a manufacturing AI solution, please drop me an email. Let's keep in touch, share our knowledge, and make this world better. Thank you.